Hey everyone, welcome back. In today's video, we are diving into the fascinating world of dielectrics, those insulating materials that are crucial in so many of the electrical devices we use every day. We are going to explore what dielectrics are, how they work, and the different types of dielectrics that exist. So, dielectrics are materials that don't conduct electricity but can transmit electrical effects. These materials play an essential role in the functioning of capacitors and other electrical components. But what makes them so special? Let's break it down. There are two main types of dielectrics, non-polar dielectrics and polar dielectrics. Let's start with non-polar ones. The non-polar dielectrics have molecules where the center of positive charge coincides with the center of negative charge. In their natural state, these molecules don't have any dipole moment, meaning there is no separation between these charges. These molecules are mostly symmetrical, such as nitrogen, oxygen, benzene, methane, and carbon dioxide. Now let's move on to polar dielectrics. Polar dielectrics are different because their molecules have a asymmetric shape. In these molecules, the positive and the negative charges are separated. They are separated through a definite distance and have finite permanent dipole moment. Examples of polar dielectrics include water, ammonia, and hydrogen chloride. So, how do dielectrics behave when placed in an electric field? Let's look at what happens when a non-polar dielectric is placed in an external electric field. When a non-polar dielectric is placed in an external electric field, the center of positive charge in each molecule is pushed in the direction of field and the center of negative charge is displaced in the opposite direction. Because of the external electric field, centers of positive and negative charges in the non-polar dielectric molecules are separated. Dielectric is then said to be polarized, even though the molecule was initially non-polar. As a result, a tiny dipole moment develops in each molecule. In fact, the force due to the external electric field pulling the charge centers apart balances the force of mutual attraction between the charges. So the equilibrium is set. Then the molecule is said to be polarized. Mathematically, the dipole moment induced in the molecule is related to the electric field by P is equal to A epsilon naught E, where P is the dipole moment, A is the constant of proportionality and is called atomic or molecular polarizability, and epsilon naught is the permittivity of free space. Let us now consider a more practical example. Imagine we have a dielectric slab placed between the plates of a capacitor as shown here. Consider a non-polar slab ABCD placed in an electric field E maintained between the plates of a capacitor. The dielectric slab gets polarized. Then the nuclei of the dielectric molecules are displaced towards the negative plate and the electrons towards the positive plate. Because of polarization, an electric field EP is produced within the dielectric, which is opposite to the E. Hence, due to the presence of non-polar dielectric, the field between the plates is reduced. This effective electric field, E effective, inside the dielectric can be written as EF effective is equal to E minus EP, where EP is the field induced by polarization. Because the effective electric field is reduced, the potential difference between the capacitor plates is correspondingly reduced, and hence capacitance is inversely proportional to the voltage. This leads to an increase in the capacitance of the capacitor. Finally, let's end with applications of electrostatics. Electrostatics have tons of real-world applications. Electrostatics, the study of electric charges at rest, is also the foundation for many inventions in technology. For example, they are essential in functioning of capacitors, which are critical components in almost all electronic circuits. These play a crucial role in power transmission. The gold leaf electroscope, a simple device used to detect electric charge, helped open the doors of research in areas like cosmic rays. and the lightning conductor invented by Benjamin Franklin is still used today to protect buildings from lightning strikes. Other examples include the working principle behind the photocopiers, where electrostatics is used to transfer the ink or toner onto paper. And of course, capacitors are everywhere, helping smooth delivery and acting as energy storage devices in electronics. So there you have it. From understanding the basic properties of nonpolar and polar dielectrics to seeing how they work in capacitors and other devices. Dielectrics are integral to the world of electronics and electrical engineering. If you like this video, be sure to hit that thumbs up and subscribe to the channel for more content. Don't forget to press the bell icon to stay updated on all of our future videos. Thanks for watching. As always, keep experimenting and exploring.